Okay, so for the procedural analysis of these kinds of problem, there are at least three things to consider when dealing with these kinds of problem. So first of all is the consideration of the FBD. The FBD. We know that the equations of motions are used to solve problems that have relationship between the forces and the acceleration of a body. So for free body diagram, the first thing you have to consider is to select an appropriate inertial frame of reference. So for instance, if the type of motion is rectilinear, the suitable type of inertial coordinate system for that is rectangular or the XYZ coordinates. Rectangular or the XYZ coordinates. So once you have selected an appropriate inertial frame of reference, say an XYZ coordinates for a rectilinear motion, once that is established, that's the time you have to draw the particles or bodies free body diagram. It is important to not skip this step, since this provides a graphical representation of all the forces that act on the body. And if you forget one or two forces that are responsible for the motion or static motion or dynamic motion of a body, then there is no chance for you to get the correct solution. So it is important to consider the FBD after selecting an appropriate coordinate or inertial reference frame. The third one that you have to consider, this one is the account for all the forces. The third one under FBD is to consider also the direction and sense of the particle's acceleration. The direction and sense of the particle acceleration. It should be established. So for most of the convention pertaining to rectangular coordinates, of course, going to the right would mean positive, going to the left would mean negative, and upward positive, and downward negative. But in the case of acceleration, you always have to think about its relation to velocity, because acceleration is only positive if it is with the same direction with velocity, and if it is only deceleration or the acceleration is only negative if it is opposing the direction of the velocity. So that's the direct relation that you should consider always. It's not about the position of up, down, or left or right, as I've also reiterated this many times from our topics in kinematics. Another one, when it comes to direction or sense, if they are unknown, so for convenience, we always have to assume the direction that has a positive sense. That is for mathematical convenience. Okay, assume always a positive sense. So the last, or probably last two consideration, once the acceleration are established, its sense and direction, then the MA vector can be used to represent the acceleration in the kinetic diagram. Yes, kinetic diagram or MAD diagram. MAD diagram, sometimes known also as kinetic diagram. You can represent the acceleration vector as MAD. the acceleration vector. You have to equate it with FBD, okay, or kinetic diagram. And last, of course, you have to identify the unknowns in the problem. So that's for the FBD. What about the equation of motion? Oh, the equation of motion, the second thing that we have to consider. I think I'll have to just add here. So for the equations of motion, if the forces can be resolved into components of the specific axis, if they can be resolved directly from the free body diagram, you have to apply the equations of motion in their scalar component form, because it's easy to operate a scalar equation than a vector equation. To always try to resolve in scalar component. If the second consideration, if the geometry of the problem appears complicated, which is usually the case in 3D, in three-dimensional motion, some type of vector analysis can be used. For example, Cartesian vector analysis. Okay, if only the problem is complicated enough and cannot be reduced to a simple type, which is a scalar component. You have no choice except to apply the vector analysis. Okay, so for still under equations of motion, considering there are many types of forces, one of the significant forces that we are always faced with is the friction. So we know that if a moving particle contacts any rough surface, it is necessary to use a frictional equation. And I think we have already discussed about the nature of the friction. There are two types, the static friction force, the kinetic friction force, and always remember that friction always acts in the direction of the velocity. So always try to include the friction if they are given. If they are negligible, then neglect them. So for the second type of origin of force is the spring. So a spring is any elastic member that stores potential energy. And for simplicity of our solving, the elastic spring is assumed to have a negligible mass, meaning their mass can be neglected. And for most type of spring, the relationship is just simple and linear, which is Fs is equals to Ks. Of course, this originates from the relationship of df. Oh, sorry. F is directly proportional to some variation, which is the displacement s. That is not a distance. So here we have K as the constant of proportionality, or the spring stiffness, and that's it. So there are springs that have different relationship. Then, for instance, Fs, we have Ks2 or Ks1/2, etc., etc. So for the most part, this is the most common relationship. So that's all for the equations of motion. Last is the, of course, but not the least, is the kinematics. Kinematics, which is the all about equation. Because in dealing with equations of motions, we're not only concerned about the forces or the acceleration, but sometimes we're also concerned about the final velocity, the total distance traveled, or the final position. So that will be useful using kinematics. So this is just to recap what we have already learned from kinematics from the past several weeks. So there are many ways to approach this one. For instance, if the velocity or position of a particle needs to be found, it is necessary to apply the principles of kinematics. Once the particle's acceleration is determined using the equation of motion. So once the acceleration is found from the equations of motion, you can use this acceleration to solve for the kinematic properties of a moving particle. So the two fundamentals equation are A dv dt, or its second form is ds dt squared, and of course b as ds dt. And the chain rule is a dv what is that? ADS, sorry. ADS V dV. ADS V dV. These are the two fundamental equations. This is just a derived equation, but this is also handy, especially if the acceleration is a function of displacement. So there are three categories of motion. One is the constant uniform motion. The second is the constant acceleration, and the third type is other than these two categories. So for the first and second type, we have already a set of equations for those. Just review them. You have already knew this set of equations. These equations are useful for other types of equation. So continue. I'd say just write the three categories, okay? For convenience, this is V constant, acceleration is constant. Here, acceleration is not constant. So under first category, we have a very simple relationship, which is V dx dt. For the second type, we have V squared plus minus 2as, V minus V0 plus minus at, and of course s is equals to V0t plus minus 1/2 at squared. And of course, for the third type, you have to use the fundamental equation to derive new type of equation. Oops. Yes. V ds dt. So after you have used this one, there is a correct way of interpreting the signs. For instance, if the solution for an unknown vector yields a negative scalar or negative value, it just indicates that the original assumption acts in the opposite direction, provided that your solution is correct. Okay, so if the final solution yields a negative scalar or negative sign, it just means that the original assumption of the sense of direction of the particle is actually in the opposite direction.